we're now covering the area of a surface of revolution. So a surface of revolution is formed when a curve is rotated about a line. And this should be extremely familiar if you've looked at volume by disk and washers. So what we're doing is we have a curve and we're going to rotate it about some axis, the X or the Y axis in this case. And that's going to give us a three-dimensional object when we rotate it. What we're doing in this section is we are now going to calculate the surface area of that three-dimensional object. So if you take a look here, if we rotate that curve over, it's going to give us this weird vase-looking 3D object, and we're going to calculate the surface area of it. Again, it should be extremely familiar if you've looked at volumes by disk and washers. I created a video on that. And what we did was we calculated the volume of that three-dimensional object. Now we're looking at surface area. And again, it's advised that you always draw a diagram of the region that will be rotated if you can do so. Okay, it just gives you some perspective and it may just come in handy one day. So let's look at how we calculate the area of a surface of revolution. Now, the surface area of the solid is going to be represented by S, S for surface area. Now, one thing to note about these formula. So note that the formula used to calculate the surface area in this section, they can be manipulated. So they are very flexible and you'll see what I mean. So they can be manipulated to a great extent, meaning that there are multiple ways to calculate the correct answer. Now, why I'm saying this is if you do some method in the examples that come up, and I've done a different method, but we get the same correct answer, that's perfectly fine. These formula, like I said, can be manipulated to a great extent. So there are multiple ways of arriving at the correct answer. But you can use the below general guideline that I've created. Let's look at it. So step one is super clear cut. It's determine the axis of rotation. And in brackets, I say use the opposite variable. What does that mean? If you're rotating about the x-axis, your surface area is going to look like that. 2 pi times the integral of y ds. Two things to note here. First thing is, what's this thing about opposite variable? So when you're rotating about x-axis, you have the variable y. When you're rotating about the y-axis, you have the variable x. So that's what I mean by opposite variable. There's always going to be a 2 pi in front. It just sits there. The next thing that I want you to take note of is take a look at what we are integrating with respect to. It's not dy and it's not dx, even though there's an x and y variable there. It's ds. What is ds? So ds is going to be determined in step 2, as you can clearly see. So what is ds? Step 2 is to determine ds, and this is where you get some flexibility. If it is easier to compute dy dx, right, that means that the equation is easily described in terms of x. Let me give you an example. So you have y is equal to 5x cubed plus x to the power 5 minus x squared, yada, yada, yada. This equation is conveniently described in terms of x. You wouldn't want to say now x is equal to something in terms of y. That would be very hard, if not impossible, to do. So it's conveniently described in terms of x, and because it's conveniently described in terms of x, it's easy to compute dy dx. If I ask you to differentiate that with respect to x, you should be able to do it. Okay, I'm trusting you should be able to do that. It's super easy stuff. Okay, so it's easy to compute dy dx. And the x limits of integration are easy to calculate. So the x limits of integration, they are easy numbers like 1, 2. They aren't weird numbers like 0.7, that's not even 7, 0.7345, whatever the case is. They're easy numbers to work with. You can work with them in integration. What are you going to choose for ds? ds is going to be this. Take a look at this. This is the arc length, part of the arc length formula. So it's the integral, not integral, square root. Square root of 1 plus dy dx all squared. Then you're going to integrate with respect to x. Now, because just something I want you to take note of. You are determining ds here, and you are going to put it in one of these, whatever the case is. Notice here that I have an indefinite integral, but when you determine ds, you are going to get limits of integration, and you can just stick those on. Remember, you're calculating a surface area. It's a number. So it's not an indefinite integral that's going to give you a function. You are going to have those limits. Right? I didn't include it here because those limits, like I said, are flexible with this section. So if you choose this ds version, your limits are going to be x values. Right. Then the converse is, not converse, the opposite. If it's easier to compute dx dy, so here it's not easy to compute dx dy, you'd need an equation that is x is equal to 5y squared minus 7y plus 100y, okay, so on. And then it's easy to get dx dy. That means that the equation is basically described easily in terms of y. And the y limits of integration are easy to calculate. Then again, ds is equal to square root of 1 plus dx dy, that integral, not integral, the derivative that is easy to calculate, square it, and then you're obviously going to integrate with respect to y. So the ds is basically part of your arc length formula, so that should be easy for you, right? And then if you can understand which one is easier to compute, you can just substitute it into there and you'll see what to integrate with respect to, because you'll have terms involving either x or y. And then from there, your limits are easy to see, because if you're using terms involving y, you know your limits need to be y values. Terms involving x, your limits need to be x values, right? And you can substitute these in place of ds there. So that's a lot of talking. Those are the general guidelines. Let's do an example. All right, exercise 1. Calculate the surface area of the solid obtained by rotating the curve y squared is equal to x plus 1, where x is between 0 and 3 inclusive and y is greater than or equal to 0, and we're doing a rotation about the x-axis. Okay, so in the first few examples, I've included a picture just so you get an understanding if you haven't already covered volumes of what we're doing. So we are rotating about the x-axis. That means here's the portion of the curve that we are rotating. Okay, that's part of the curve y squared is equal to x plus 1. So it's going to get rotated and it's going to look like that. It's going to look like that. Okay, so it kind of looks like, what does this look like? It looks like a bucket, probably. So it looks like a bucket. There we go. Okay, and then you've obviously got the portions in the back. Okay, so that's what we have. We get this three-dimensional object when we rotate it. And we are going to get now we are going to have to calculate the surface area. So the surface area here, all on the top, all on the bottom, and in the back. That's what we are trying to do. Okay, so now that we know what we are doing in a picture, let's actually go ahead and calculate it. So the first step, step 1, is to check the axis of rotation. We are rotating it about the x-axis. Therefore, I'm going to choose s is equal to, remember, opposite variable, 2 pi integral of y ds, not dy, ds. Step 2 is to choose what ds is. Take a look at the equation. Y squared is equal to x plus 1. I'm going to rearrange that equation, and it's going to become, so I'm going to rearrange that equation. It's going to become x is equal to y squared minus 1. Take a look at this equation. It's conveniently described in terms of y. So it's x is equal to terms of y. So since that's the case, I can get dx dy pretty easily. So dx dy, that's going to be 2y. Differentiate this with respect to y. Okay, if you don't believe me, what I suggest you do is try and get dy dx from this equation. So solve for y and try and get dy dx and check how easy that is to obtain. Okay, it's much easier to get dx dy. Okay, so I have dx dy, and since I have that, ds is going to be square root of 1 plus dx dy all squared. And because it's in terms of y, I have terms of y, I'm going to integrate with respect to y. That means I'll use y limits. In fact, what I suggest is don't even memorize this. Once you work that out, just remember the arc length formula. You took your first derivative. This is technically a first derivative, and then you sub it in your arc, part of your arc length formula. Okay, so that's what we're going to do. So let's get rid of that. All we need to do is square it. We will get plus 4y squared, integrate with respect to y. So the surface area is now going to become, that looks like an integral. It's S for surface area, 2 pi, the integral from, let's take a look at the diagram. We need y limits. So it's going from y is equal to 1 to y is equal to 2. So we're going to have 1 and 2 there. And then we had y. Okay, then we have 1 plus. Remember we had ds here. So instead of writing ds, I'm going to replace it with this portion here. It's going to be the square root of 1 plus 4y squared. Integrate, obviously, with respect to dy. And this is just a standard integral. Okay, we can use substitution on this. I'm just going to integrate it. So it's going to be equal to 2 pi. All right, let's integrate. So this is going to become half. So it will be 1 plus 4y squared to the power 3 over 2 multiplied by 2 over 3. And then we're going to have y divided by derivative of the inside. That's going to be 8y. Okay, and then we're evaluating it from 2 to 1. Okay, let's evaluate that. Okay, so the y's are going to cancel off. This is 3 times 8, 24. So, and then we have a 2 here. So that is 2 over 24, that's 1 over 12. And then we have 2 pi over 12, that's going to be pi over 6. So it's pi over 6. And then we are left with 1 plus 4y squared to the power 3 over 2. And then we are evaluating it from 1 to 2 rather. So it's pi over 6 into, let's substitute 2 in. 2 squared, 4. 4 times 4, 16. Plus 1, that's 17. 17 to the power 3 over 2. Then sub in 1. 4 times 1 squared is 4. Plus 1, that's 5. So it's plus 5. Sorry, not plus, minus 5 to the 3 over 2. Okay, there's your answer. If you want it in terms of units, you can use a calculator, but this is your final answer. You can leave it like that. I'll just give it to you in terms of units so you understand what's happening. It's going to be 30.846 units squared. That's the area of that surface of revolution.